Okay, so this will be the fourth lecture over NMR spectroscopy. So in this one, we're going to go into a little bit more depth into the theory. So we talked about some of the basics before. So all nuclei carry a charge because they have protons in them, so they're all positively charged. And some nuclei, right, this charge spins on the nuclear axis, which generates a magnetic dipole. And we talked about that before, right? If it's spinning this direction, if you wrap your fingers in the direction of spin, then it's got a magnetic moment vector in that direction. Or if it's spinning that direction, if you wrap your fingers in the direction of the spin, then it would have a magnetic moment in that direction. So the angular momentum of the spinning charge can be described in terms of a quantum number I. So I can have values of 0, 1/2, 1, 3/2, 2, 2.5, so forth. So if I equals 0, then that nucleus has no spin. And the significance of that, if it has no spin, then it's not NMR active. So it's only nuclei with I values that are not 0 that are NMR active. So the spin number I can be determined by the number of protons and neutrons in the nucleus of the atom. So there's 4 scenarios, right? You can have number of protons odd and the number of neutrons even, in which case you would have an odd mass number. So those nuclei will have I values of 1/2, 3/2, 5/2, so forth. So examples would be H1, tritium, nitrogen 15, fluorine 19. Or you can have even number of protons and an odd number of neutrons, then those nuclei are, so you'd have an odd mass number, so those nuclei are NMR active as well. They have I values of, again, of 1/2, 3/2, 5/2. So examples of that would be carbon 13, oxygen 17, silicon 24. So they would all be NMR active. Or you could have an even mass number. So two ways you could have that, right? You could have an odd number of protons and neutrons. And if that's the situation, then your I value is 1, 2, 3, or 4, a whole number. They're NMR active. So examples of that would be deuterium or nitrogen 14. And the other scenario is when you have an even mass number, you could have an even number of protons and an even number of neutrons. And in that situation, then I is equal to 0, and those nuclei are not NMR active. So examples would be carbon 12, oxygen 16, sulfur 34. So you can do NMR on lots of different nuclei. As we'll talk about, some of them are easier to interpret than others though. So in organic chemistry, most often we're dealing with hydrogen, carbon, oxygen, nitrogen, or one of the halogens, fluorine, chlorine, bromine, iodine, or sulfur or phosphorus, right? So of those elements, so hydrogen 1 is the most abundant isotope in nature. It's 99.9885% hydrogen 1 in nature, and that's NMR active, right? It's got an I value of 1/2. Carbon obviously extremely important in organic chemistry, otherwise it's not organic. So it's unfortunate that the main isotope of carbon is carbon 12, which is not NMR active because it has an I value of 0, so it does not have nuclear spin. But you can do NMR on carbon. You just have to look at the carbon 13 isotope instead, but there's only 1.04% carbon 13 in nature. Oxygen, obviously organic compounds often have oxygen in them. So again, the main isotope of oxygen, similar to carbon, is oxygen 16, which is not NMR active. So there is an isotope of oxygen that is NMR active, but that's only 0.038% in nature. And for nitrogen, so the main isotope of nitrogen in nature is nitrogen 14. So you can do NMR on nitrogen, but the problem is that I is equal to 1, and as we'll talk about, that makes the NMR much more complex. So it's difficult to interpret. Fluorine only one isotope of fluorine in nature, fluorine-19, and it has an I value of 1/2, just like hydrogen. So understanding fluorine NMR is extremely analogous to understanding proton NMR. So we can do all of these NMRs at NM on our instrument if we wanted to. So chlorine, a couple of isotopes that are NMR active. It's very common for people to do phosphorus 31 NMR. And bromine and iodine are all NMR active as well. So obviously organometallic chemists and inorganic chemists, they can use NMR as well. So there are many other non-metals or metalloids or metals that are NMR active. But interpreting their NMR spectra may not be as easy or as useful as it is for carbon and proton NMR. So one of the reasons behind that is the I value. So if I is equal to 1/2, then that nucleus has a uniform spherical charge distribution, and those are the simplest NMR spectra to interpret. So proton H1 has an I value of 1/2, for example. So if I is equal to 1, so for nitrogen, we said nitrogen 14 has an I value of 1. So they have non-spherical charge distribution, so they have what's known as a quadrupole, and that leads to much more complex and much more difficult NMR spectra to interpret. So if the I value, value determines the number of spin orientations given by this equation, 2I plus 1. So if I is equal to 1/2, so 2 times 1/2 plus 1 equals 2. So if I is 1/2, there's only 2 different spin orientations of the nucleus, and so that's what we've been talking about. So it's either rotating like this with the magnetic field in that direction, so clockwise, that would be counterclockwise from my perspective, or clockwise from my perspective, in which case its magnetic moment would be in that direction. So that would be the 2 nuclear spin states that we're talking about. Okay, so we've used this diagram before to illustrate the nuclear spin states. So in the absence of an external magnetic field, those nuclear spin states are equal in energy. But when you put the proton in the presence of an external magnetic field, then those 2 nuclear spin states are no longer equal in energy, right? Where you could have if the magnetic field's in that direction, then if your proton is spinning in this direction, its magnetic field is in the same direction, so it's aligned with the field, right? So if you remember, that's called the alpha state. Or if your magnetic field's in this direction and the nucleus is spinning that direction, then its magnetic field is opposed to the applied field, and that's the beta state, which is higher in energy. And so we've talked briefly about this before, but we'll talk a little bit more about this today. So you can calculate the energy difference between the alpha and the beta spin state using this equation. So it's equal to this constant. So gamma, which is the magnetogyric ratio, which is specific to an atom, to an element, times Planck's constant times the strength of the magnetic field divided by 2 pi. All right, so obviously as the magnetic field gets bigger, then the energy difference between the nuclear spin states gets bigger. Okay, so the magnetogyric ratio is the fundamental nuclear constant. For every nucleus has its own value. So for proton, its value is 26,753 inverse seconds, inverse Gauss. So 1 Tesla is equal to 10,000 Gauss. So if we calculate the energy difference between these spin states, so if we want to see what the frequency is, right, so delta E is equal to h nu, and delta E is also equal to this. So if we set those 2 equal to each other, then Planck's constant cancels out. So the frequency that's needed to cause a nuclear spin flip then is given by this equation, the magnetogyric ratio for the nucleus under question times the strength of the magnetic field divided by 2 pi. So also see that difference in energy is extremely small between the alpha and beta spin states. So at any one time, there's obviously more nuclei in the alpha state, but the beta state is populated as well. There's just more nuclei in the alpha state than the beta state. Okay, so if we were on a 2.5 Tesla magnet instrument, so if we calculate what the difference in energy between the alpha and beta spin state is, so plug in the magnetogyric ratio for proton, 2.5 Tesla magnet, convert from Tesla to Gauss. So that would give you a frequency. So the frequency is 1.06 times 10 to the 8 inverse seconds. And then if we convert that to megahertz, so that would be, you would need 106.4 megahertz energy to flip a proton from being aligned with the field to against the field. So that would be at 100 megahertz NMR. Or so if you double the strength of the magnetic field, you double the frequency. Right, so if it was a 5 Tesla magnet, then that would be a 200 megahertz NMR. Okay, so we've talked about UV vis spectroscopy, IR spectroscopy, and NMR spectroscopy. So let's talk about the energy difference between the ground state and an excited state. So for UV spectroscopy, so if we're talking about a pi to pi star transition, right, the ground state would be both electrons are in pi. And then if you hit it with the right frequency radiation, then you can excite an electron from pi to pi star. So then that would be the excited state. So the difference in energy from pi to pi star, if it's 254 nanometer radiation where that molecule is absorbing that, then that's about 113 kcal per mole. So in IR, so if we're talking about a ketone, for example, how much energy is required to stretch a carbon-oxygen double bond? So that's about 1700 inverse centimeters. So that's 5.88 microns. If you convert that to energy, that's about 4.87 kcal per mole. So comparing UV to IR, right, 4.87 divided by 113. So to cause the molecule to go from the ground state to the excited state in IR, which is the vibrational mode, it only requires about 4.3% as much energy. So much easier to excite a molecule in IR, the vibrational mode, than it is to promote an electron to a higher energy orbital. For NMR, let's say you're on a 500 megahertz instrument, so the difference in energy between the alpha and beta spin state is only 0.477 calories per mole. So if we compare the energy difference between the alpha and beta state, the ground state and the excited state in NMR, to UV vis, so if we take the energy between alpha and beta state in NMR divided by the energy for the pi to pi star transition in UV vis, then that it causes an excitation in NMR, you only need 0.00042% as much energy to flip the nuclei from the alpha to the beta state. Or comparing NMR to IR, to flip between the alpha and beta state versus cause the bonds to start vibrating only requires about 0.01% as much energy. So the basic point is, in NMR, very little energy is absorbed to cause the molecule to do a nuclear spin flip. So it's either absorbed, or when the molecule relaxes back to the ground state, it's emitted, which is actually what's measured, right? So only very little energy is being absorbed or emitted. Basically what that means is you need a very sensitive detector to measure those small energy changes. So what does that mean? That means it's very complex electronics involved, and that means it's a very expensive instrument. So this just tries to put that in more of a graphical form, right? The energy difference between the pi and pi star is quite large for UV vis, and so the significance of all of that, because the energy difference between the excited state and ground state is so large, all of the molecules are in the ground state. So without shining the UV light on the molecule, none of the electrons are in pi star, they're all in pi. Okay? So that means every single molecule is available to absorb UV radiation. Same for IR, the energy difference is still quite large. So all of the molecules in IR are in the ground state. So every single molecule in that sample is available to absorb the infrared radiation to be excited. But in NMR, the ground state and excited state, alpha and beta states, are so close in energy that there's a significant number of protons aligned against the magnetic field at any time. There's more in the alpha state than in the beta state, but there's a significant number in the beta state. And we're going to calculate that, show you just how many nuclei are actually in the excited state, even without the radio frequency radiation. They're just naturally in the excited state because the energy difference between ground state and excited state is so small. So we can calculate the number of nuclei in the alpha and beta state using what's known as the Boltzmann distribution. If you've taken physical chemistry, you've probably heard of that before. Okay, so this is the math. So N beta over N alpha is the number of nuclei in the beta state divided by the number of nuclei in the alpha state. So that's equal to E to the negative difference in energy between the alpha and beta state divided by K, which is Boltzmann's constant, and the temperature. And we've seen this equation before, right? Delta E is equal to H nu, and it's also equal to Planck's constant times magnetogyric ratio times the strength of the magnetic field divided by 2 pi. Okay, so if we take these equations and then combine them, then we can come up with this equation. So the ratio of protons in the beta state versus alpha state is equal to Planck's constant times magnetogyric ratio times the magnetic field. So this is a calculation for a 300 megahertz NMR divided by Boltzmann constant and the temperature in 2 pi. Then we get E to this negative 0.00004835. So the ratio of nuclei in the beta state to nuclei in the alpha state is 0.999952. So what does that mean? So that means if you had 2 million protons, then if there were 999,976 in the beta state, so aligned with the magnetic field, in the absence of any energy being applied, other than whatever energy is just available at room temperature. And if there are 1,024,000 in the alpha state, then that would give you this ratio, right? So if we just subtract these numbers, this is the number in the alpha state, number in the beta state, so 1,024,000 minus 999,976 gives you 48. So what does that mean? That means there's 48 more out of 2 million protons. There's 48 more in the alpha state than in the beta state. And so what you need to do is you need to excite those to the beta state. So basically what that means is there's only 48 nuclei out of 2 million that are available to absorb this energy, so that you can see the energy difference. So 48 out of 2 million is times 100%. So 0.0024% of the protons in the sample are available to do a nuclear spin flip to right. So basically what that means is there's not many nuclei that are going to absorb or emit the energy, because when they emit the energy, they're going to go back to this state, right? So you're going to basically have 48 nuclei out of 2 million that's going to be emitting that energy, and you have to detect that energy. So you need to amplify the signal, and you need to have a very good detector. So there's a lot of electronics involved in NMR, and it's very expensive electronics, and it's very complex electronics. So to maintain the instrument, you need somebody with a lot of electrical engineering knowledge. So maintaining an NMR can be quite a large expense, because you need somebody with a lot of expertise that knows how to do that kind of stuff. Okay, so in terms of NMRs, 900 megahertz to 1 gigahertz NMR is about as big as you can get to maintain a uniform magnetic field. So that's going to max out how much electricity you can put into a wire before ripping it apart. Okay, so we talked about concentration in NMR before. So NMR is typically done at millimolar concentrations in about 0.75 mils. So if we took 1 millimolar times 0.75 mils, converted millimoles to moles, and Avogadro's number of molecules per mole, so that would be how many molecules are in an NMR sample. But there's only this fraction of them available in the alpha state. That's right. That's the fraction that's available to absorb or emit this energy that you're going to detect. So out of that 4.52 times 10 to the 17 molecules, only 1.83 times 10 to the 13 molecules are going to be given the signal in the NMR. So if we compare that to UV or IR, so we said all of the molecules in UV experiment start in the ground state. So if we took that number, that's how many are in the ground state in UV or IR, and divide that by the number of molecules in NMR that are going to be available to give rise to the signal, then UV or IR, there's 25,000 times as many molecules available to absorb the radiation. So again, it just illustrates the significance in NMR that you need really good detectors and amplify the signal in order to see the signal. Okay, so let's go back and talk a little bit about more carbon NMR. So we made the point that carbon-12 is not NMR active, right? It's unfortunate because that's 98.9% of carbon in nature, but it does not have nuclear spin. So carbon-13, only 1.07% in nature, natural abundance. Its I value is 1/2, so you can do NMR on it, which is not too difficult to interpret. And then of course there's carbon-14 in nature, but there's only very minor amounts of carbon-14 in nature. It's radioactive and only available in parts per trillion concentration. So this presents a practical problem doing carbon NMR, right? As in proton NMR, it's 99.985% natural abundance versus carbon, 1% natural abundance. So that means right off the bat, carbon-13 NMR is only 1/100th as sensitive as proton NMR. But it's further complicated by the fact that for carbon-13, the magnetogyric ratio is only 1/4 that of proton. So what's the significance of that? If you go back to the Boltzmann distribution, magnetogyric ratio is there in the equation, right? So for carbon, if this value is 1/4 that of hydrogen, then that means the energy difference between the alpha and beta spin state is even smaller. And so what does that mean? That means there's even a smaller ratio of protons in the alpha to the beta state, so there's even fewer carbon atoms that are available to give a signal in proton NMR, because when they relax back to the ground state, there's not going to be that many relaxing back to the ground state because the beta state is not that much higher in energy than the alpha state. Right, so the magnetogyric ratio affects the Boltzmann distribution. So overall, the sensitivity, when you combine these two, the overall sensitivity for carbon-13 is about 5,700 times as less sensitive as proton NMR is. So what that basically means then is you need more sample for carbon-13. You need to have it a lot more concentrated, right? Because if there's two carbons in the molecule, well, there's not a high statistics of there being any carbon-13s in the molecule, right? And because of the Boltzmann distribution, right, you need a really concentrated sample to do carbon-13, or you have to go to really long acquisition times. So you can do a proton NMR in 5 minutes. Carbon-13, if it's really concentrated, maybe a couple of hours, or if it's at the same concentration as your proton NMR, then you're going to be doing 1 or 2 days worth of acquisition of data in order to see the signal. Okay, so let's talk about this nuclear spin flip in a little bit more detail. So if we okay, so if that's a proton spinning, so And if this is your magnetic field, so it depends on the magnetic field, and that's the proton spinning. The point is, so one point to recognize it, it's the magnetic field of the proton is not perfectly aligned with the magnetic field of the pen, or the external magnetic field. It's maybe slightly tilted a little bit, and so what happens is this proton precesses about the axis of the magnetic field. So if this is the proton, and it would have, if I wrap my fingers in the direction of it and its magnetic field was in that direction, the point is they're not perfectly aligned. It's tilted a little bit, kind of like a top, and then it precesses around the magnetic field of the external magnet. So that's what this diagram is trying to illustrate, is that proton precessing about the magnetic field of the external magnet. So the proton wobbles around this axis, right? Okay, so each of these lines then that I have drawn here represents a different proton, but it would be protons in a molecule such as. So we're going to talk about this molecule in a little bit more detail in a minute. So maybe it's a bunch of those molecules, and maybe it's these two hydrogens, for example, which are equivalent. So it's a bunch of those hydrogens, each one's a different hydrogen, but they're all equivalent to each other. So they're all precessing about this y-axis. Okay, so we have our XYZ Cartesian coordinate system here. So we have the magnetic field is in this direction. So that's from the NMR instrument. So it's in the y direction. And the protons are precessing about that y-axis, right? Kind of wobbling like a top. So then what we have is radio frequency. So we have a radio frequency generator. And so radio frequency is a form of electromagnetic radiation, right? So if you have electromagnetic radiation, so if that's its electric field in pink, then all electromagnetic radiation has a magnetic field that's perpendicular to it. So that's what's in blue here. So what we're going to use is the magnetic field of the radio frequency. And so what's going to happen is when the frequency is just right, what's going to happen, so we've been using this diagram, which is not quite accurate in NMR, because we're not actually going to spin flip it. What we actually do, what's actually done in NMR, is you're just going to take that proton and you're just going to knock it over. So when the radio frequency is just right, then those protons will absorb this energy and they will tip over at 90 degrees. And so it's the magnetic field of the radio frequency, and then that's going to cause this to tip over. So what the ideal is to tip at 90 degrees, and so now you have those nuclei precessing about the x-axis. So that's the excited state. So that's the alpha. So that's the alpha and the beta state that we've been referring to. So we're not actually flipping the spin totally against the external magnetic field. We're just knocking the protons over 90 degrees. Okay, so again, in this diagram, it's useful to teach this at a very fundamental level, because this is certainly a lot more complex. But we are changing this spin state from being aligned somewhat with the magnetic field, although that it's precessing about that magnetic field, to being knocked over 90 degrees, and now it's precessing about the x-axis. But it doesn't stay there, right? It would like to go back to being aligned with the magnetic field. Okay, so let's talk a little bit about this molecule. So there's two kinds of protons in that molecule, HA and HB. And so they would be precessing about the magnetic field, the external magnetic field. They would be precessing about that at different frequencies. So which is precessing at a higher frequency? Well, that would be the one that requires higher energy to do a spin flip. So which one is going to require more energy to do a spin flip? That would be HB. So HBs are represented here, HAs are represented here. So they're each precessing about that y-axis at a different frequency. And then of course in NMR, what you do is you scan frequency from low frequency to high frequency, or high frequency to low frequency. And so when the frequency is just right, then these will you'll knock these over, and you're going to knock HAs over at a lower frequency than you knock HBs over. Okay, so once they're knocked over, then what do? How do they relax? So eventually they're going to relax and go back to precessing about the y-axis. So there are two different relaxation pathways that are typically talked about. So one's what's called T1 relaxation. So this is where the protons are going to transfer energy to protons nearby in space. So that would be the ones that are not on the same carbon as themselves. So they can transfer, it doesn't have to be to other protons, they can transfer the energy to something else rather than the hydrogens that are on that same carbon. So that's what's called T1 relaxation. So T1 relaxation will reestablish the alpha state. So they'll basically go back to be precessing about the y-axis, and then they can be excited again, and then they can relax again. So T1 will, how long T1 is will determine how many, right, how much signal you're going to acquire in a given amount of time. Right, so the more scans that you can acquire in a given amount of time frame, that's going to increase your signal to noise ratio, right? Or you can have what's known as T2 relaxation. So this will be where you transfer energy between protons on the same carbon, and that would be a bad thing, right? So if this represents CH2 hydrogens, for example, so a bunch of different HBs precessing about that nucleus, ideally all at the same frequency, all at the same rate. So if they start transferring energy between each other, then, so if we just focus on two of them, for example, two protons, both of them are HB, initially precessing about the same rate, but then they start transferring energy between each other. So one will slow down and one will speed up. So then they'll be precessing at different rates, and that's what's called dephasing. So that's what happens in a T2 relaxation process, and that would be bad because that's going to lead to, so HA would, okay, so this diagram's for HA, would initially be a triplet, right? So if these are all HAs precessing about that nucleus, and then they get out of phase where some are precessing fast and some are precessing slower, what happens in that case is you start to lose information, because now your triplet starts to look like that, and if it gets out of phase enough, then your triplet looks like that. And the significance of this is you've lost information, right? If you no longer know that it's a triplet, then you no longer know how many neighbors it has, and so you've lost structural information. Okay, so relaxation rates are slow in NMR. They take anywhere from 0.1 to 100 seconds. So once a proton's excited, to relax again, so that then you can scan it again. So proton carbon-13 relaxation times can be even worse than that. So if you compare that to UV vis and IR, their relaxation is on the order of micro or pico or femtoseconds. So as soon as you excite that electron to a higher energy state, it's going to want to drop right back down to a lower energy state much faster, UV vis compared to NMR. So basically that means longer acquisition times in NMR. Experiment takes longer. Okay, so one of the things you do when you take an NMR, you shim on the sample. So what's going on if you shim? So this is our NMR tube in pink, and we have this molecule dissolved in some solvent. And then we have, so this represents in green the big magnet, and so it has magnetic field lines that we're representing like this. And so the goal is for molecules at the top of the flask, the NMR tube, in the middle of the NMR tube, and at the bottom of the NMR tube to all be in the exact same magnetic field, because you want all of those nuclei, and you want them all precessing no matter where they're at, about at the same rate. Otherwise you get, right, poor NMR spectra. So in order to make sure you have a homogeneous magnetic field from top to bottom, then you have to shim on the instrument. So what that means, basically, so there's small magnets on the big magnet, and you're going to change the current to those instruments. So you're going to change the magnetic fields of the small magnets, and you're going to use those magnetic fields to try to straighten out or make the big magnetic flux lines as homogeneous as possible from top to bottom of the instrument. Right, so you want all of the CH2s and all of the CH3s, if we're talking about ethyl chloride, to experience the same magnetic field no matter where they set in that NMR tube. And that would be another reason why you spin the NMR tube when you're acquiring the spectra. All right, so if you have good shims, you may see a spectra that looks like that. If you have poor shims, then your signals are going to be broad, which means you've lost some information, right? You still have chemical shift, but you have no idea if it's singlet, doublet, triplet, quartet, so you have no idea how many neighbors that particular proton has. Okay, and then lastly, if we talk a little bit more about carbon relaxation rates. So carbons with hydrogens attached to them relax faster than carbons without hydrogens attached to them. And so the significance of that is that messes up integration in carbon-13 NMR. So in proton NMR, you integrate, right? You acquire your NMR, and you integrate the area underneath, and it tells you it's a 3, so maybe that's just a CH3, or maybe it's 3 equivalent CHs, so that's information, right? But in carbon NMR, integration is basically useless. And the reason why is because carbons relax at different rates. So if you have a carbon that you knock over and then it relaxes, and you can knock it over again and it relaxes, and right, the more times it does that, then the more signal you get, and you acquire multiple scans and then average all of those scans, right? So if you have one carbon that's relaxing fast and another carbon you knock it over and it takes a long time for it to relax, well, you're not going to acquire as much signal for that carbon. And basically what that means is the signal is not going to be as strong. So just to illustrate, so if we took a molecule like this, so carbons with hydrogens on them relax faster. So you're going to knock it over, it's going to relax, and you're going to measure that energy that comes off, and you're going to knock it over, it's going to relax, and you're going to measure that energy that comes off. So for the CH3s, they have 3 hydrogens on them, they're going to relax faster. So their signals are usually much stronger in carbon NMR. CH2s with 2 hydrogens versus a CH, so in this case they're both just one carbon, but one's taller than the other because one's relaxing faster, so you're acquiring more data on it. And then carbons with no hydrogens, they relax the slowest, so their signals are going to typically be the weakest in carbon NMR, and you may have to do a lot of scans, right, several hundred or thousand scans before those signals start popping out of the noise in the baseline. So they don't have hydrogens on them, so they relax slower, so they're not going to, you're going to knock it over, and then it's going to take forever to come back to the alpha state, and then you have to knock it over again, but you're not going to acquire as much data, so their signals are going to be much weaker. So even though you can't integrate the area, but you can still look at the relative intensity of the peaks, and that gives you some information about the signals. CH3s are usually the biggest, and carbons with no hydrogens are usually the smallest. And then of course, if you have equivalent carbons, then that's going to enhance the signal as well. Just like here, E's are equivalent to each other, so that's going to enhance their signal as well. Okay, we'll stop there.